2. How far did we get last time? 45? 43? I think I did 43.
I think you did 43 and then went back and did 38. And I think that's where we ended.
Yeah. So 45 is just the same as 44. Did we do 44, 45?
I'm pretty sure you did 44.
The only thing there is you make 2 products. So you have 2x on the top squared instead of just x squared on the top. Okay. There's so many other equilibrium questions yet to come that let's just move on. So 51 is what happens to each of the following. What happens to the equilibrium at each of the following? So it shows you a couple of SO2s, sulfur dioxides, they're gases, and an dioxygen in equilibrium with a couple of molecules of sulfur trioxide. And it tells us in the question that delta H is less than 0. What does that mean? The value of delta H is less than 0.
Exothermic?
That means it's exothermic. Exothermic reactions have negative values for enthalpy change. So that is exothermic, which means it gives out heat. So one of the cheap things that we can do heat is a product. Endothermic reactions have heat as a reactant. Exothermic reactions have heat as a product. Okay, what happens to each of the gases when the following happens? A, O2 gas is added to the system. Well, O2 is a reactant, so if you up the pressure of oxygen, you push that way. The reaction mixture is heated. So if you add heat, one of our symbols for heat is the triangle. That means heat. You add heat, well, heat is a product. That means now that you have too many products, you are upping the equilibrium here at that position, which means it pushes back that way. The volume of the reaction vessel is doubled. Doubling the volume, keeping everything else the same, is going to lower the pressure. And we learned, let's look at the delta N change in numbers. So we have 3 gas molecules on the left and 2 gas moles on the right. So that is 2 minus 3. I have a negative value for delta N. An increase in pressure always favors the side with the least number of gas moles. That's the way we learned it. So decreasing the pressure will push to the left. Okay, then it starts to get a bit tricky. A catalyst is added. Catalysts make the forward and reverse reactions work equally well, so that has absolutely no effect. It might make equilibrium position get reached a little bit earlier, but it doesn't change the position. And then a noble gas is added, and that noble gas is going to increase the total pressure of the system. Now that reads a little bit deceptively, because increasing the pressure should favor the side with the least number of gas moles, and you'd be forgiven for thinking that. But because you are making up that pressure with something else, and that gas is not part of any of this, then it doesn't enter into this equation. So if I added argon, argon is inert. It'll be on both sides. I mean, it kind of evens itself out. And then the last one, what if you removed sulfur trioxide? Well, sulfur trioxide is a product. If you remove product, your equilibrium will shift to make more product. Okay. All right. And then 16. Ooh, nice pen. I'll have to keep that one. 1618 says, designate the Lowry-Bronsted base on each side and tell me which one is the conjugate acid, conjugate base, blah, blah, blah. Okay? So, I got HBRO plus H2O makes H3O plus and BRO minus. What you have to remember is that acids give away H plus and they make H plus and the conjugate base. So the conjugate base always has one less hydrogen and one more negative charge. So that gets to be the conjugate base, which means that is the acid. So in this particular reaction, HBRO is acting as the acid, it's hypobromite, and hypobromic acid. And water is acting like the base. In the presence of an acid, water will behave like a base. And it gets to be the conjugate acid. The conjugate acid has one more hydrogen and one more positive charge. There's 3 of those in a row. You should just be able to work through them. They're just descriptive. Which of the following is the strongest? And then they give you a list. Well, the one with the most number of oxygens. If we're looking at oxo acids, the first one is an oxo acid. It's chloric acid and hypochloric acid, or chlorous acid rather. So it's chloric acid and chlorous acid, and one of them has 3 oxygens. So all the contents are the same, but one of them has more oxygen than the other. So in oxo acids, in ternary acids, those with 3 types of atom in them, the most number of oxygen is going to give you the stronger acid. Okay. And then 1629, calculate the H plus for each of the following solutions and indicate whether it is acidic, basic, or neutral. Okay. And 1629 and 1637 are the same question. What 1637 does is some of the times it gives you H plus, some of the times it gives you OH minus as a concentration, some of the times it gives you pH, and some of the times it gives you POH. So you should be able to figure that out. Let's do one of those. So I'll do 1637. Do you have any preference? Look at 1637. If you've done it already, or tried it already, and said, I really didn't like that one, A, B, C, or D. So what you're supposed to do for 1637 is fill in the missing numbers. Okay?
Can we do C or D?
Yeah. So I got an H plus concentration. The brackets for my OH minus are missing on the table. And then pH, POH, and then a question. Is this acidic or is it basic? All right, so if we do part C, that tells me that the pH is 8.25. Go ahead and fill in the missing numbers. Okay? So pH is negative log to the base 10 of the H plus concentration. So 8.25 is negative log 10 to whatever that H plus is. Which means, look where on your calculator the log button is. We're going to be a number that is raised to the power of 10 there's a negative right there. So that's your exponent button. So whether you put the number in first and then hit exponent, on the old calculators I would do that, on the new ones, where the math is visually perfect, you would do EXP to the negative, 8.25, and that would reveal what the value of H plus is. I don't know what the answer is. If I still had my solutions manual, I could look it up.
We can look this
No.
up.
Yeah, let's. While you're working, I can cheat and look up the numbers.
Okay, I got 5.62 times 10 to the negative 9.
Okay. 5.6
62
times 10.
to the negative 9.
Okay. 1637. All right, the other thing that you can do straight off the bat, the easiest thing to do, is if I've got the pH in this column of this table, what's POH?
14
POH is 14 minus pH. You should come up with that one straight away. Now, the other way, so now we have two ways of getting, once I put this number in, because that's what I just found, I have two ways of finding this number. I can use this number right here that I'm reasonably confident I did right, or I can use that number that I'm absolute certain is correct. What am I looking at? 5.6 times 10 to the negative. Yeah, that's correct. Okay. So I've got this. Now, I can get to this number here by saying KW equals KA times KB. No, this time. Blah, 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 blah. That's not what I would, it was on my mind, but that's not going to help. This. Okay? And that equals 1 times 10 to the negative 14. Or I can go this way. Same thing, that because this is POH, right? POH is negative log to the base 10 of the OH concentration. That means that OH concentration is 10 to the negative POH. So this 5.75, hit the exponent key, it'll put a number right here. Or this number means that all I have to do, which one am I finding? This one. Which means that is 1 times 10 to the negative 14 divided by my 5.6 times 10 to the negative 9. They both should come out as being the same number.
Do we just know that number off the top of our head?
The 1.0 times 10 to the negative 14?
Yeah.
Yes. That's the basis of your 0 to 14 pH scale, with 7 being in the middle. Water does this. It's the auto-ionization of water. It splits apart a tiny amount. That is 1 times 10 to the negative 7 moles per liter. This, of course, has to be the same value. And when you combine those together, because K for this is products divided by reactants, but my reactant is a liquid, so I just get what's called the ion product. It's only these two multiplied by each other. And 1 times 10 to the 7 times 1 times 10 to the negative 7 both times, is 1 times 10 to the negative 14. Yes, that's a number you're supposed to know.
In this situation, though, we could use either one. We'd either use the 5.75
Yeah.
or do that.
Yeah.
Okay.
So one of these numbers spawns all the other ones, and this one out here comes out to be 1.8 times 10 to the negative 6. And these two have units because they're concentrations, and the pH and the pOH do not have units because there's a log in there, and that makes the units go away. Okay? If you can do it for one of them, you can do it for them all. Okay, and then 1643 starts out really simply. It says calculate the pH of these acids, and I got 4 different questions, sub-questions. The first acid is HBr, which is hydrobromic acid. Is that strong or weak? Strong. The second one is nitric acid, HNO3. Is that strong or weak? Strong. The third one is HClO4. Strong or weak? Strong. That's about as strong as you can go. That is perchloric acid. The central atom, chlorine, is electronegative, and then it has 4 oxygens around it. This is very, very acidic. Then the next question is a mixture of HBr and HCl, 2 strong acids. This question is about strong acids, and to know the pH of a strong acid, you just know the molarity of the acid, because the acid is going to dissociate 100% in solution. So whatever concentration I tell you the named acid is, that's how much H plus is in solution. Okay? So let's do the most difficult one. They start out, here's a named concentration of an acid. Tell me what its pH is. That's straightforward. Take that number, take the log of it, and then turn it from being a negative number to a positive number. That's your pH. The next one gives you gram amount of nitric acid. You have to turn the gram into moles by taking the formula mass. Grams divided by formula mass equal number of moles, and then divide by volume. I can do that one for you. And then the third one is a volume, but a times a concentration, diluted 2, that's M1V1 equals M2V2. The fourth one is the most complicated. You're mixing 2 acids together. So what you should do there is find the number of moles in both of the individual solutions, and then find the total volume of the mixture and divide the number of total moles by the total volume. All right, let's do a couple. This is something that is quite simple, but I've said before, we have graduated students who are very good at chemistry, but cannot do simple dilutions. Can't do them. And there's no reason why. It's kind of silly. And at some point, someone is going to yell at you in lab. How come you can't do this? Who did you have for general chemistry? And you're not going to tell them my name. So we are going to do it. This is 1643. All right, find the pH. Let's do part B. We'll do part B, and then we'll do part D. I've got 1.52 grams of HNO3 in 575 milliliters of water. Okay, here's what you need to know. Number of moles is mass divided by formula mass. Molarity is moles per liter. M1 V1 equals M2 V2, and pH is negative log to the base 10 of the H plus concentration. For this first one, we don't need the M1 V1 equals M2 V2, but we will need it for the fourth one. Okay, there's my mass, formula mass. That's a 1, that's a 14, that's 3 times 16. 16, 32, 48, 52, 62, 63. 63 what? What are my units for formula mass?
Grams.
Grams per mole. Number of moles is mass divided by formula mass. So I have 1.52 grams divided by 63 grams per mole. The grams cancel and the per mole goes to the top. I don't know what the number is. What question is this? 43. And we're doing... Yeah, I still don't know, because the book has done it a different way. Okay, if you say so. I don't know. I'm trusting you. All right, got my number of moles. Now I want molarity, and molarity is the number of moles per liter. Here's my number of moles. How many liters do I have?
0.575.
There are 1,000 milliliters in a liter. So moles per liter gives me this. What is that number? Yep. Okay. This is a strong acid, nitric acid, HNO3. All nitrates are soluble, all of them, every last one of them, because nitrate is a powerful electrolyte. When it goes into solution, it splits apart and it has no interest in recombining. Means this is an exceptionally strong acid. So, think about initial, so I'm not at equilibrium. But I can do initial and final. At the point that I dissolve the nitrogen trioxide in water to make HNO3, at the very, very, very beginning, I have 0.042 moles of this. And none of that has been made yet. At the end, what do I have? How much HNO3 stays in solution? None of it. None of it. Strong acids dissociate 100%. So all of that goes away, which means I have a nitrate concentration in solution of 0.042 moles per liter, but I have an H plus concentration in solution of 0.042. Yeah? Okay. What was the question? Find pH. pH is negative log to the base 10 of the H plus concentration. This number is less than 1.0. Therefore, the log of this number is a negative number. That negative in front of the log will turn it into a positive number. And because this is nitric acid, it had better be lower than 7. Your answer should be lower than 7. 0.042 is dilute. So I'm not expecting this number to be 1, but I am expecting it to be a small number. I don't know what number it is just yet. Oh, okay. The number that you get is? 1.4. There's something, I don't know if we're going to do it in lab, but there's a thing that you can do, and we have pH meters that will really help with this. I used to do it just with universal indicator paper. If you take a big beaker of water and some dilute acid and just put 1-2 drops of acid into that solution, the indicator turns. That's all you need for the pH in that beaker to plummet. You put a buffer in there and just pour the acid in, and it just stays where it is. The pH stays static. Yeah, huge swings in pH. It's a log scale. Huge swings in acidity with small volumes. Okay, let's do the last one, because the last one's the most complex. Those of you who likes doing dimensional analysis, where you put everything in the calculation all at the same time? Because we could have done that. I broke it down, find the number of moles, find the molarity, find the answer, okay? I like breaking things down into chunks and following the logic of my process. But there's no reason why we could not have put the input was in grams and the output needed to be in pH. Okay, so we would have turned grams into moles by multiplying it. You do 1 over its formula mass. That would give you grams, turn it into moles, and then we would multiply the number of liters, milliliters into liters. We would have put a conversion in. I don't like doing it that way. I'm not going to go back and reinvent that question. Part D. Part D says you are going to mix together 2 solutions. We're going to mix 10 milliliters of 0.1 molar HBr and 20 milliliters of 0.2 molar HCl. Now there may be another way to do this where it's all in one calculation. Let me see how the book does it. No, they do it the way that I do it. They just stuck the 2 pieces together. Yeah. We're going back to this. Molarity is the number of moles per liter. So, this question tells me volume and molarity. And I know that at the end, I'm going to have a total volume of 30 milliliters. Okay. So I'm going to take my molarity is moles per liter, and I'm going to rearrange it so that the number of moles is molarity times liters. Take that liters, move it across the equal sign, it comes up over here, it isolates the N on its own, okay? And I'm going to call this number 1 and number 2. I'm going to find the moles in 1, moles in 2, and then divide back into the total in the total volume. So, in 1, the number of moles is 0.100 times 10.0. And in 2, number of moles is 0.200 moles per liter times 20.0 milliliters. Ten times 0.1 should equal 1. This has 3 significant figures. That has 3 significant figures. Okay. 0.2 times 20 2 times 20 equals 4. Because 2 times 2. We've done this before. It's like, why are you talking about numbers when they're not the numbers that are in the question? Because it doesn't matter what you do with the numbers, as long as you rectify where the decimal point is. 2 times 2 is 4. So your numbers are 4. The only question is, where's my decimal? This is 2 above and 1 below. So I end up pushing up, right? Okay, so total. I have 5 moles going into 30 milliliters. And molarity is moles per liter. So molarity is moles per liter. So the total number of moles is 5, and the total number of liters 0.030. There are 1,000 milliliters in a liter. So 1 liter, 1,000 would be here. 300 milliliters would be that decimal point. 30 milliliters would be this decimal point. So 5 divided by 0.003. Yeah.
If we convert that one to liters, why didn't we convert that part to liters?
Oh. Yeah, we should have done that.
Can it still be not converted over there and we don't have to do that whole thing?
I don't know. It seems reckless, and I wouldn't approve of it. That's clearly not right. Let me look at my numbers. Yeah. So yeah, this is not milliliters. This is now this is liters. I had written it here as liters. My bad. So this is 0.100 10. Okay. Still going to be this, but it's going to be further down the decimal. And instead of being 20 milliliters, it is 0.0200 liters. My bad. Okay, so where is my decimal now?
.00.
Yep. Yeah. Okay. This is going to be better. That number would have given me a very large molarity. So when that number would have come out, and you said, I would have a very, very large molarity, and I would have recognized immediately, that cannot be right. Okay, 5/3. All right, so that molarity is the molarity of my HCl/HBr, but they disappear 100% to make H plus and Br minus. Therefore, this is also the concentration of H plus. I want to know the pH. Take that number, take the negative log to the base 10 of it. Now, I have two very, very strong acids. Dilute, and that's moderately dilute. So I'm expecting a very small number. If that number is less than 1, I wouldn't be surprised. And the number is?
0.78.
Okay, let's move on and look at some equilibria questions from this set. So 53 and 56 are similar. 55's in the middle and is a little bit different. It uses percent ionization as the first step. I don't think that's very common, but it's not particularly difficult. So 53, 55, 56 is they're all similar to each other. 59, 60 are the same question as each other and are asking for everything. So that needs a solution that is all-encompassing. Let's pick 2 of those at random. And then the last one on the list is what we started in lecture this morning. Percent ionization at 2 different concentrations. One of them is going to be straightforward. The second one is probably, let me read it. It's actually 3 different concentrations. The first one is 0.25, and then the last one is 0.02, and I'm going to guess that the last one requires a quadratic solution. So, has anybody attempted between 53 and 60 and would like clarification on any of those? Because they're in 2 different sets, but they're pretty much the same question.
So if we went through one of these and one of them has a quadratic, like you have to find a quadratic solution, we're not gonna be tested on that?
No, I'm not going to put it on the test.
Okay.
No, it's just going to, that will just chew up time. Okay, I told you in lecture, learn to recognize it. There might be a question somewhere that says, what would you do? How would your solution have to be different if the concentration was very, very small? And the Ka is now reasonably big. Yes, it would require a quadratic. I said in lecture, I wouldn't sit down and do it with a pen and paper, because these days you don't need to. Faced with that, I would stop, I would open Google, and I would find an online quadratic solver and put the numbers in. So
if you did ask us, it would be like a conceptual question?
Mhm.
Okay.
yeah,
For 55,
yeah.
how do you use the percent ionization?
Yeah,
And
so-
what do you use it to find?
So the percent ionization of a weak acid is the concentration of H plus divided by the concentration of HA. And that is the initial concentration of HA and the equilibrium concentration of H plus. So the H plus can be found here. So 55 tells us, there you go. Okay. The question, this is 1655, tells us that a 0.100 molar solution of chloroacetic acid, I'm not going to write chloroacetic acid out, I'm going to just call it HA, is 11% ionized. From that, I'm going to expect you to find H plus, A minus, HA, Ka. This one doesn't ask for it, but you could give pH as well. Okay. So let's go. Right from the beginning, 11.0 equals my H plus concentration, don't know what that is, divided by 0.100. That leads me directly to the equilibrium concentration of H plus, which will tell me how much out of the my value of X, right? We'll write out an initial change at equilibrium. So H plus is 11 times 0.100, which is 1.10.
Maybe 0.11 for 11%.
Okay, so times 100, it's 11. Thank you. So I'm going to divide all of that by 100. So this goes under, that goes up. Yeah, so it's turning out to be a kind of a big number. So the 100 is above the line, it's going to end up being below the line. This is below the line, it's going to end up being above. There you go. So 11 times 0.1 and then divide it all by 100. So that gets to be 1.1 and then 0.11, 0.011. I think, haven't looked in the book yet, but that looks right. Okay, so HA turns into H plus and A minus, and this was for chloroacetic acid. Don't know what the value of Ka is, but I do know a couple of the numbers now. I know that I have an initial, I have a change, and I have an equilibrium value here. My initial value is 0.100, and this is a 0, and that's a 0. This grows at plus x, that grows at plus x, this goes away by minus x, and then this is 0.100 minus x, and this is x, and that's x. But I just found out what the value of x was. So I can take my eraser, look, it's right here. The value of H plus, equilibrium concentration of H plus, is also the same as the concentration of the conjugate base. So we know what those values are. This is 0.011. This is 0.011. And now this is 0.100 minus 0.011. This question is the complete backwards interpretation of the way that we would normally do this question. We'd normally give you some numbers and then say, go find me Ka, and go, oh, here's the Ka and a number. Go find me the H plus, the pH, and percent ionization. This question is working backwards, but the numbers can go forwards and backwards, no problem. So K, products divided by reactants. This is 55. Let me just make sure I'm on the right track. Yeah. Okay, so on the top, I have 0.011 times 0.011. That's 0.011 squared. And then underneath it, I have 0.100 minus 0.011. chloroacetic acid is fairly strong. No, it's still a weak acid. It's going to classify as a weak acid. It's going to be in equilibrium. It's not going to dissociate 100%. But the addition of that extra chlorine in the molecule means that it's got extra electron withdrawing ability. That extra electron withdrawal makes the oxygen to hydrogen bond even weaker than normal. Makes that H plus fall off. So this number right here,
0.0014.
I'll write it out that way, 0.0014, or 1.4 times 10 to the negative 3, 1, 2, 3, 3 zeros. So in terms of a value of K, that's fairly big. We've seen times 10 to the negative 5, times 10 to the negative 8, times 10 to the negative 10, some of these things, and still be acids. That one's reasonably large. So our pH should also be fairly small.
And 1.96.
Okay. For how much concentration? 0.1 molar solution? That's pretty good. Okay. Let's do one of the ones at the bottom. 59 and 60 are kind of the same question. They give you a concentration and the value of Ka. So we're just going to do what we did, but backwards. Okay. Any preference, 59 or 60?
60.
They're in pairs on purpose so that we can do one, you can practice with the remaining one. The Ka for chlorous acid is 1.1 times 10 to the negative 2, which is I don't think that's necessary. I think you should really only do it in multiples of 3s. I don't like that at all. We're asked to find the equilibrium concentrations of H plus chlorite and undissociated chlorous acid at equilibrium. For a 0.0125 molar solution. Okay. So we have done this. We have worked through this particular process multiple times in class already. Okay, you should be familiar with this question this way. HA dissociates into H plus and A minus. And I I know my initial concentration. And the initial concentration of these two is a 0. And at equilibrium, they will split apart into equal concentrations that all were sourced from this number right here. And because that number is, this molecule is splitting apart, I'm going to lose X number of molecules to gain X number of cations and gain X number of anions. Okay, what's next? K. Ka is H plus times A minus over HA, which is X times X, so X squared, divided by 0.0125 minus X. Uh-oh. Might have put this one on the list. Might have put this one on the list. 60 is different than 59. In 59, question 59, the Ka is 6.3 times 10 to the negative 5. And the concentration is 0.05 moles per liter. In this one, the concentration is 0.0125, that's kind of dilute. And the Ka is big. The Ka is only 0.01. This is not looking so good for us. Now, the numbers in the 10th edition and the 13th edition, so this question has a Q behind it because the numbers are slightly different. The concentration here in this question is 0.0125. In the 10th edition, our book, that concentration is 0.0075. That's even more dilute. They have still allowed the approximation to go ahead with the same acid. Oh, you know what? They've cheated. They changed the value of K. They went from chlorous acid to hypochloric. Boo. Yeah. So they changed the identity. So what they've done, and I don't blame them. This is the way that the educational process is going. Is we're taking the really difficult questions out of the book because students don't like doing them because they're not good at doing them because they don't have the math skills. Okay, this one is going to grind to a halt at this point because Ka is 0.011 and these numbers are not 100 times bigger. Okay, this concentration is not 100 times bigger than that one. So this has a quadratic solution. And it's not in the solutions manual because the solutions manual is running a different question. Okay, let me take a pen. Who's got a pen?
And does the answer sound like 0.00745, you think?
Did you solve it with a quadratic?
Yes.
Let's take a look. I'll work it out.
Yeah, for X.
That's what I got.
Yeah. The concentration.
Okay, I'll write it out. So what we would first have to do is break this up, okay? So x squared over 0.0125 minus x equals 0.011. Take all of that over. 0.0125 minus x equals x squared. Multiply that out. So this 0.11.
1.375 times 10 to the negative 4.
And that's just the number, and then that's the x. Okay, and then we move these over so that it equals 0, and I have 0.375 times 10 to the negative 4 plus 0.011. That gets to be C, this gets to be B, and the 1 that's here gets to be A. And then I mean, you can continue on paper, but it's 2018. Do you do them by hand, CJ, or did you?
No, I didn't.
Do you know how to? So, do your calculator has a program? Yeah. I would do it on the program, or I would Google quadratic solver. And I just pump those numbers in. I am not doing this by hand. I didn't like them when I was a student, and I still don't like them now. So, and that came up with an answer of what?
X equals 0.00745.
Yeah, it's not going to be a desperately small. It's not going to be a desperately small number. Those two numbers are similar to one another. Okay. All right, sorry about that. So 1659 would be one like we've seen 100 times before. That one, yeah, 1660 is a quadratic. And my guess is that when you look at 1666, the first part is a regular solution. The second part's probably a regular solution, maybe. And the third part is a quadratic.
I had to use a quadratic for both B and C.
Because, yeah, I think that's probably right. Although, this one, again, is not showing it. So 1666. Let me see if the numbers are the same. So Ka you would have to look up in the text. Actually, Ka for this propionic acid, which is now called propanoic acid, is this number you unfortunately have to look up in an appendix, is 1.3 times 10 to the negative 5. So that puts me 1, 2, 3, 4, 5. You could sneak by with an approximation of all three of these. Yeah. You would squeak that last one. You would squeak it. Let's do one. It was all going to hinge on what the magnitude of the Ka was. And propanoic acid's Ka is small enough that we can get by. So this is called prop. Prop means 3 carbons. Has a Ka that is, what did I just say, 1.5 times 10, something like that? 1.3 times 10 to the negative 5. Why they couldn't write it in the question? Because how many words does it take to say Ka is given in Appendix D? That's more characters than saying Ka equals 1.3 times 10 to the negative 5. Okay. Let's do the middle one. When the concentration of the free acid is 0.0800 moles per liter. This one's gonna be all right. This is almost 0.1 molar, and I'm looking at 10 to the negative 5. So 0.000013, that's the value of my Ka. My concentration is going to start to be a problem. This would be 10 times, that would be 100 times, right about here. Right about there. So as long as I'm 0.1 or 0.01, I'm okay. But anything less than that, and I'm not gonna be allowed to approximate anymore. And all my numbers in this question, they start out at 0.25 and they go down to 0.003 or 0.03. They go down to 0.03, which is still here. Okay. Still be more than 100 times bigger than the value of my Ka, so I'm allowed to keep my approximation. Okay, all right, done this many times. Initial, change, equilibrium. Initial value is 0.08, nothing and nothing. This goes up by plus x, this comes down by minus x for all the reasons that we've described many times. 0.0800 minus x equals x. X. Ka is 1.3 times 10 to the negative 5, which is equal to x squared for 0.0800 minus x. Because the value of Ka is more than 100 times smaller than the value of my concentration. this contribution to my calculation, this value here, x, is not going to be significant. And I can approximate it out of existence. So x squared over 0.08 equals 1.3 times 10 to the negative 5. Therefore, x squared equals 1.3 times 10 to the negative 5 times 0.08. X squared equals whatever that number is. Therefore, the root x is equal to the root of whatever that number is. And of course, x represents h plus. So 1.3 times 10 to the negative 5 times 0.08 equals
1 times 10 to the negative 6. It's 1.04.
Okay, well, 13/8. You know what your 13 times table is about 100. So that probably makes sense. Okay, take the root of it. Instead of being 10 to the negative 6, now it's going to keep all the digits in your calculation, don't round them up. Should be about 10 to the negative, so
0.001.
it should be about 10 to the negative 3, so 0.001 now, 10 to the negative 3. And that's going to be equal to the h plus. Unless we've got any rounding errors in here, those numbers are now good enough to be used. So, equilibrium values of HA is 0.08 minus 0.001. Only changes that number right there. Okay, and then it asks for percent ionization. Okay, percent ionization. We did this a little while ago in the reverse direction. That is the equilibrium concentration of H plus divided by the initial concentration of acid, all multiplied by 100. So that is 0.001 divided by 0.08. And it's not going to be a lot. Those are going to cancel. Those are going to cancel. And now it's like 1 in 80. 1 out of every 80 is about 1.2. So you should be be looking at about 1.2%. Oh, we've got to multiply it by 100. Not a lot. Okay, now there are two other components to this. 1666 Part A and 1666 Part B. In Part A, the concentration of the acid is larger. What do you think that does to the percent ionization? Percent ionization between, comparing two acids. One is more dilute than the other. So in Part A, it is the most concentrated. In Part B, it's in the middle. And in Part C, it is the most dilute. Which one has the greatest percent ionization?
The most concentrated one?
The dilute one. We did that on the board today, first thing, and we changed 3% to 40% or something like that. I can't remember what the numbers were, but it was a big difference. As you make your acids more dilute, they become more efficient at ionizing. The total number of H pluses in solution is not more, but each individual HA does a better job at splitting apart.
If it's a lower. That makes sense.
More dilute equals more percent ionization. It's the first thing that we did today. It was also the last thing that we did on Thursday. All right. Study this problem set. I have a feeling that some of these are going to appear on tomorrow's test. I haven't written it yet. Yeah, I know. It'll be warm off the photocopier in the morning when you get it. Don't let anybody ever tell you, I've got a copy of Maguire's test. No, I haven't written it. Don't lie. Okay. See you all tomorrow. And